welcome you to the Dallas Independent School District STEM Environmental Education Center. Teachers, if you're watching and you have not signed up, please go to www.tiny.cc/EEC register and sign up, please. This is just for our attendance records. Program this morning will be components of the universe. During this virtual field trip, students will describe components of the universe, recognize that the sun is a medium-sized star located in a spiral arm of the Milky Way galaxy, and that the sun is many thousands of times closer to Earth than any other star. And identify how different wavelengths of the electromagnetic spectrum are used to gain information about components in the universe. Mr. Monroe will discuss components of the universe. Mrs. Nash talk about the HR diagram. Mr. Maris will explain the sun, and the electromagnetic spectrum will be discussed by Mrs. Fuller. You cannot ask questions verbally, but you can go to www.tiny.cc space EEC question /EEC space question space answer, and send us a question. We'll do our best to answer them during the field trip, the virtual field trip. But if we can't, I will send the answers to your teacher, and your teacher can discuss them with you. Now I'm going to stop sharing my screen, and Mr. Monroe is going to tell you all about components of the universe.
Good morning, students. My name is Mr. Monroe, and we're going to be looking at components of the universe. Wow. I've got a short time to cover a lot of area. In fact, the observable universe contains roughly 100 billion galaxies, each containing millions to billions of stars. And we know that our sun, that furnishes heat and light energy to the planet Earth, our planet, is the center of our solar system. Can you just imagine what's out there? You know, we step out at night and look into the dark sky, and we see lots of light sources, stars, all kinds of things we notice in that night sky. It's almost like looking at something I want to show you. And I want you guys to remember that I showed you this, because I'll come back to it at the end of the presentation. Here I have a container that has soap suds, and I'm sure all of you guys can see that, hopefully. Now, it consists of, I don't know how many bubbles in here, but this is almost like looking at our universe. It's so massive that we can't really count the number of objects and items that are in our universe. Okay, now I'm going to readjust the camera. Now, something else I want you students to do, there's a couple of questions that I want you to be able to answer, or maybe your teacher will have you answer those, or give some information about the statements that are going to be made. So you might want to take notes as we go through the presentation. Number one, I want you to be able to name and describe at least 5 components of the universe. Number two, I want you to be able to tell the difference or describe the difference between a nebula and a galaxy. Those 2 things, and probably more that you will hopefully remember, I want you to be sure to be able to complete those 2 tasks. So I'm going to stop right there and start sharing my screen, and we're going to use a little PowerPoint that is called Power Notes. What happened there?
That's the Zoom meeting you're already in. You don't want to
I don't want to do that. Well, it looked like it kicked me out.
I think you might want to click on where it says My Drive at the top there to the left.
Yeah. Okay, there we are. Our place in space. You know, what makes up the universe? Earth is one of 8 planets that orbit the sun, which is a star. And remember what I said about there being billions, millions, and billions of stars that are members of different galaxies? Well, can you imagine other solar systems existing? Just, it's unimaginable. In fact, there's a favorite phrase that I like to use, and that is, it's more than a notion. You know, a star is a large celestial body that is composed of gas and it emits light and heat energy. Stars are grouped together in structures known as galaxies. A galaxy is a large collection of stars, gas, and dust. There are an estimated 100 billion galaxies in the universe. Boy, that's a lot. The universe is space and all the matter and energy in it. Remember, space and all the matter and energy in it. Earth is a special place because it has just the right combination of conditions to support life as we know it. The presence of air and water supports the growth and development of plants and animals. The atmosphere contains an ozone layer that absorbs harmful solar radiation and other gases that keep Earth warm enough for life to exist. The solar system is a collection of large and small bodies that orbit our central star, the sun. The solar system has 8 bodies called planets, which are generally larger than other bodies. A planet is a spherical body that orbits the sun. The 4 planets that orbit nearest to the sun are what we call terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, and Mars. The terrestrial planets are rocky, dense, and relatively small. The 4 planets that orbit farthest from the sun are called gas giants. The gas giant planets are Jupiter, Saturn, Uranus, and Neptune. The gas giant planets have thick gaseous atmosphere, small rocky cores, and ring systems of ice, rock, and dust. Orbiting most of the planets are small bodies that we call moons, sometimes referred to as satellites. Earth has only 1 moon, but Jupiter has more than 60. Wow. The solar system has other bodies, small bodies, including dwarf planets, comets, asteroids, meteoroids. Altogether, there are up to 1 trillion small bodies in our particular solar system. A star is a large celestial body that is composed of gas and emits light. Most stars are composed almost entirely of hydrogen and helium. Energy is produced in the core of the star by the process of nuclear fusion. And that goes back to a lot of people used to believe that actually there was a lot of burning going on the surface of the sun or the star, but it is created in the core. Energy escapes from in the form of light, other forms of radiation, heat, and wind. Stars range in size from about the size of Earth to as much as 1,000 times the size of the sun. A galaxy is a large collection of stars, gas, and dust held together by gravity. Small galaxies called dwarf galaxies may contain a few billion stars. Giant galaxies may contain hundreds of billions of stars. Our solar system is located in the Milky Way galaxy. The Milky Way galaxy is classified as a spiral type galaxy. Spiral galaxies are shaped like pinwheels they have a central bulge from which two or more spiral arms extend. Elliptical galaxies look like spheres or ovals and do not have spiral arms. Irregular galaxies appear as splotchy, irregularly shaped like blobs. There are very active areas of star formation. Distances between most objects in the universe are so large that astronomers measure distances by using the speed of light. A light year is the distance that light travels through space in 1 year. Light travels through space at about 300,000 kilometers per second, or about 9.5 trillion kilometers in 1 year. And that would be the unit of measurement used as a light year. The universe can be defined as space and all the matter and energy in it. Throughout the universe, there are areas where galaxies are densely concentrated. These areas are called clusters and superclusters. Clusters contain as many as several thousand galaxies. Wow. Superclusters can be made up of 10 or more clusters of galaxies. Unbelievable. The universe also contains huge spherical areas where very little matter exists. These areas are called voids. Astronomers have begun to think of the universe as having a structure similar to soap bubbles. Now, students, that's why I showed you the dish with the soap. Can you imagine soap bubbles and being able to count just those soap bubbles I had in that little dish being compared to the universe? Wow. Clusters and superclusters are located along the bubble walls. Astronomers believe that is a comparison. The interior of the bubbles are voids. It takes light hundreds of millions of years to cross the largest voids. Unbelievable. And I'm going to stop sharing my screen and show you that soap bubble, those soap bubbles again. Just imagine our universe. Now, there's one more thing that I want to cover with you because it is actually the answer to one of your questions, and that is, what is the difference between a galaxy and a nebula? Well, students, listen. A nebula may form from a star, as in the case of a planetary nebulae or supernova remnants, or be the actual birthplace of a star. So a nebula would have dust and gases possibly left over from a supernova, or it might even be the beginning of a new star. Want you guys to have a good day today. And if any of you have any questions, I think Dr. Gorman probably can answer those for you. All right, Dr. Gorman.
Thank you, Mr. Monroe. And one thing that just kind of boggles my mind is when you're talking about the distance and the time involved in the study of astronomy. We think 100 years is a long time. That's not even a soap bubble when compared to how long it's been since the Earth was made and the sun was made. Okay, the question is, what is the biggest component of the universe? All right, the biggest supercluster known in the universe is the Hercules Corona Borealis Great Wall. It was first reported in 2013 and has been studied several times. It's so big that light takes about 10 billion years to move across the structure. For perspective, the universe is only 13.8 billion years old. Again, those numbers are just amazing to me. And now, Miss Nash is going to tell you about the HR diagram.
Hello, welcome to my classroom. Today we're going to be talking about the HR diagram. Otherwise, we know it's the HR diagram, but we can also call it the Hertzsprung-Russell diagram after the two fellows who just developed it. And it's one of the most important tools that we have to study the evolution of stars. Right? So we're going to look at some pictures here and think about what it tells us. And share. It doesn't show out. And there we go. And there we go. It's been a while since I've done this. So, and Esnar, Hertzsprung, and Henry Rose Russell independently developed the diagram, this diagram. But they both did the same thing. They plotted spectral type temperature versus stellar luminosity. And they saw trends in the plots. It was not random. So in 1911, that was a long time ago, more than 100 years ago, Danish astronomer Esnar Hertzsprung, that's him on the bottom right, okay. He compared and plotted the magnitude of stars with their color temperature. They just been able to have new telescopes that allowed them to do some more, get more data. In 1913, American astronomer Henry Norris Russell plotted stars spectral class against their magnitude, and that's him on the left. This is him right here. He was at Princeton. So my pop quiz question is, can you find Denmark on the map of Europe? And my research question for you is to discover the relationship between Greenland and Denmark. And where's Princeton? Can you find Princeton on the map? Can you find New Jersey? Okay. How big is New Jersey? Not very big. Here it is compared to the state of Texas. So just an aside. So it's a graph that plots the surface temperature of stars against their brightness. Okay. So it's pretty easy to make a graph like that. And what you discover when you do that, the stars are not random. They're in groups, okay? And this one example shows some kind of common favorite stars, beginning with our sun right here, the North Star Polaris here. So this is what we call the main sequence. Most stars turned out, one of the first things they noticed when they started doing this is that most of the stars were in this one line, kind of going diagonally down. And that's because, that's why they call it the main sequence. Then we have some down here, the white dwarfs, up here, the giants and the supergiants. And you can find a few of our other favorites like Betelgeuse, okay. And here's another favorite, Deneb, okay. So you can, if you have a little telescope or even just a pair of binoculars, you can find some of these stars and think about where they are on that diagram and why they're where they are. So why are they where they are? Well, because this is the temperature down here, okay, from hot to cold. So when we think about blue, we think, oh, it's a cool color. So if we're decorating a room or making a painting, blue tends to be cool for us. The color of water, the color of the sky. But in terms of a flame, if you have a fire or even a match, the blue part of that flame is the hottest part, okay? And that's why these are the blue, okay? And they go down. So we think of red as being a really hot color, but in terms of stars, the red are the cooler stars, okay? So interestingly, so these are little small stars down here. They're cool, probably because they're just small. But then we also have these giant things like famously Betelgeuse up here, okay? That's also, oh, come back. There we go. It's also cool, but it's so gigantic. It's so gigantic, okay, that we can still see it, okay? And then, so our biggest ones are these blue stars, okay, yeah. So cool but bright up here, like Betelgeuse, okay, remember? Okay, over here, hot and bright, the supergiants and the giants. So and then the white dwarf. So our sun will be going through a life cycle. So we imagine our sun starting off in the main sequence. It's burning hydrogen, but when it runs out of hydrogen, it's going to start burning helium. And then it's going to expand to a huge size and become a red giant. Okay. Then, after it runs out of helium, it's going to become a white dwarf. Now, they're very hot, okay, but because they're so small, okay, they're not very bright. No, okay. So stars have a life cycle depending on how much mass is in the initial star formation stage. The protostar, if it's some average size, it'll come up here to our sun, and then our red giant, then a planetary nebula, and then the white dwarf. If we have more mass in the initial protostar, we can get a more massive star. And then as it runs out of hydrogen and begins burning helium, it will form a red supergiant. Now that one, because it's so gigantic, has so much mass, it will begin burning other things besides helium. And finally, when it runs out of everything except iron, it's going to explode as a supernova. Okay. And then it will end up as a neutron star or even a black hole, depending on how much mass was in the initial, started out with. Okay. So the usefulness, one of the kind of main things about the HR diagram is that it can follow each star through evolutionary stages. Okay. And we can see that our predict, so this one, Betelgeuse, must have started out as a more massive star, okay, up here. Okay. So we can infer its past and we can also infer its future. So it's a very useful tool for science. So kind of amazing that these guys so long ago were able to figure this out, and we still use this diagram as a tool to study stellar evolution. Okay, I'm going to stop sharing here. Okay, so that's all I have for you about the HR diagram. I also have some little models I made here of the stars. So this is our sun, and this would be a hotter star. Remember, the colors, okay, are kind of opposite of what we kind of think in our daily life. So blue stars are the hot ones, okay. The red ones are cooler, but if they're supergiant, they still are giving off a lot of light just because of the size of the star. Okay, thank you. And if you have any questions, Dr. Gorman would be glad to answer.
Thank you, Ms. Nash. And we do have a question. Actually, with two questions. Give a brief description of the HR and where does our sun fit on it? Ms. Nash did a great job of explaining all about it. So we're going to give you a brief definition. Now, this is according to Britannica. I always like to give credit for somebody when they've done the research on this. On the diagram, stars are ranked from the bottom to the top in order of decreasing magnitude. That means increasing brightness. And from right to left by increasing temperature. Stars of the galactic arm in which the sun is located tend to fall into distant regions on the diagram. The group called the main sequence extends in a rough diagonal from the upper left of the diagram to the lower right. The giant sequence of large, bright, though cool stars appear on the upper right, and the white dwarfs, dim, small, and very hot, lie in the lower left. The sun lies near the middle of the main sequence. And now, Ms. Ramirez is going to tell you all she knows about the sun.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about the sun. So before we get started, I just want to show you guys a quick little model of the sun. And this is just a super easy paper model, but you can see some of the layers of the sun. So you can see the internal structure. We also have the super bright corona, the outer light area. And then just to give you guys an estimate, or just to put it into perspective how big our sun is, if the Earth is the size of this dime, then the sun would be the size of a doorway. So that's just how massive our sun is. So I'm going to go ahead and share our screen with you guys, and we'll start our presentation. The first thing I want to show you guys is if you are interested in making a sun model, it's a free paper model from Canon Creative Park, and the link is on the website. But it's a really good model to help you guys understand the internal structure and the layers of our sun, so that you can compare the layers of our sun compared to the layers of our planet Earth. So again, the link is provided on the slide. So today we're going to be learning about the sun, and I have a couple of essential questions for you guys. So hopefully by the end of this presentation, you guys will be able to answer these two questions. The first question is, how is the sun different from a planet? And the second question is, how far away is our sun and where is it located in our galaxy? So keep those two questions in mind as we go through the presentation today. So as we learned earlier, our sun is simply a star, and it is a mid-sized star. It's a main sequence yellow dwarf star. So we learned about the HR diagram in the previous segment. So see if you can find where our sun is located on the HR diagram. And hopefully you guys remember that it is just a mid-sized yellow star, so it would fall here along the main sequence stars. So here's our sun, which is the star, and then we have a planet, and that planet happens to be Jupiter. So take a moment to compare and contrast characteristics of a star and a planet. So you can feel free to pause the video if you would like to allow time for discussion. I'm going to go ahead and tell you guys some of those differences. So when we talk about a star is simply a large celestial body composed of gases. And most of those gases are going to be hydrogen and helium. And something very important, a big difference, is that stars actually can produce energy by nuclear fusion. And this fusion, this energy can actually escape as light, heat, and radiation. So that's a big difference between a star and a planet. And that is, stars can actually release energy, and they can actually produce light. And then also our stars can have orbiting bodies such as planets around them. So think about our very own sun. Our sun provides light and heat for planet Earth, and it of course has the planets in our solar system orbiting around it. Now, in comparison, a planet can be rocky or terrestrial, and it can be, or it could be a large gas planet like we see in the picture with Jupiter. And again, the biggest difference is planets do not produce their own light. So that's the biggest difference between a star and a planet. So now we're taking a look at just how massive our sun is. You can take a moment to look at these different diagrams and see if you can make any observations about the size comparison between the sun and various objects in space. So I thought some of these graphics were very eye-opening, just to help give you guys a good idea of how massive our sun is. So if we take a look at this picture over here, we know that it takes about 109 Earths laid across together to equal the diameter of the sun. So that's quite massive. And if we compare the sun to Jupiter, you could fit about 1,000 Jupiters inside the sun. And then of course we know Jupiter is our largest planet that we have. And then you could put about 1,300 Earths inside of Jupiter. And then if you take a look at this little picture over here, you can see another good size comparison where Earth is just the dot and the sun is that big, massive star. And again, just remember, if the dime represents planet Earth, then the doorway would represent the sun. So again, huge size comparisons. And the sun's volume would need about 1.3 million Earths to fit it. So again, the sun is massive. And so where exactly is our sun located? So take a look at this diagram here and see if you can figure out the name of the arm of the Milky Way galaxy where we can find our sun. So hopefully you guys are able to find it. And we do know indeed that our sun is located in the Orion spur or arm of the Milky Way galaxy. And sometimes on a super clear night, you can even see a part of that Milky Way arm going across the sky, as you can see in this picture here. And our sun is located near the edge of the galaxy, and it's about 93 million miles away from Earth, and we simply call that 1 AU or 1 astronomical unit. And as far as the location also within the galaxy, it is about 1/3 the distance from the center of the Milky Way galaxy. So we learned earlier about galaxies. The Milky Way is a spiral galaxy. So we can see the bulge here, and then we can see those spiral arms. And we know that the sun is actually the closest star to Earth. How far away do you think the next closest star is? So I'm going to show you guys a little video from YouTube, and it will actually put into perspective just how massive our universe is. Oops, let me go back and see if we'll play. So again, make note that the sun is 8.3 light minutes away from the sun. So notice we haven't come across any stars yet, any other stars. So we're now at 1 light year away, and we still haven't come across any neighboring stars. It's not until we're at least 4.2 light years away that we reach our closest star. And I'm going to stop the video there. So our closest star is about 4.2, 4.3 light years away, and it's called Proxima Centauri. So if you take a look at this diagram over here, you can see some of our other close stars. And when I say close, we're talking about they're still many light years away from us. So here's our sun right over here. Here's our 5 light year mark, and you can see that we do have a little cluster of stars. We have Proxima Centauri right over here. That's about 4.3 light years away. And then we have some other stars by it, Centauri A and Centauri B. We also have Sirius over here, and that's actually a really bright star. And then you can see some of the other neighboring stars. But again, notice the distance. They are still quite far away. And then in our next thing, I just have a couple of last minute slides that I want to show you guys. So on your own time, I want you to visit these 2 websites. The first one is solarsystemscope.com, and the other one is an article from BBC. So let me show you guys what they look like. So let me get out of this. This first one is, oh, it says there's an error. Okay, well, we're not going to be able to show that one because it doesn't want to show for us right now. Oh, maybe it will. So this one normally takes a while to load, so we'll see if it'll load for us. But this one is solarsystemscope.com. You can visit this one, and it will actually give you kind of like a virtual simulation of the solar system. And let's see if it will let us go. So take a moment on your own time, go to this website. You guys can, let me turn off some of these sounds. You can go visit the sun. You can read about the sun, learn about its structure, its internal structure. You can see 3D models about the sun, so you can learn about those different structures. And then we were talking about the actual stars closest to the sun, so we can also visit some of those stars. So if we take a look at our near stars over here, you can see this map with some of our close stars, and obviously the length of the line, the shorter the line, the closer that star is to the sun and Earth. So here we have, which I didn't know this before, but Rigel Kentarius is actually the scientific name for Proxima Centauri. So Proxima Centauri is part of a triple star system. So apparently there's common names for stars, and then there's also the scientific names. So just keep that in mind when you're looking at some of these names for the stars, but you can see some of those other ones, and then you can even visit those stars and get information about them as well. So you can see Alpha Centauri, also known as Rigel Kentaurus, and it's a yellow dwarf star. So you can visit this website on your own to explore other stars within our solar system. And then this other one is from BBC. It's How Big is Space Interactive, and it will take you on a virtual exploration through Earth. So you start out in a rocket on Earth, and if you keep scrolling all the way down, you'll see just how far out distance-wise things are. For example, the highest skydive, the highest living organisms. You can see what's in different parts of the atmosphere all the way until you get all the way out to some of our planets and things like that. So that's something fun that you guys can research on your own. So I'm going to stop our screen share, and that's all I have for you guys on the sun. We're going to give it back to Dr. Gorman to answer any questions.
Thank you so much, Mr. Maris. And we did have a question. The student says, you told us the distance, you told us the size, you told us all about it. But now we're kind of concerned about one thing. How much longer is it going to last? You know, because we know that if there's no sun, we've been told that if there's no sun, there's not going to be any humans. Okay. So it's estimated, according to www.space.com, it's estimated about 5 billion years. But in about 5 billion years, the sun will run out of hydrogen. Our star is currently in the most stable phase of its life cycle and has been since the birth of our solar system about 4.5 billion years ago. So we don't have too much to worry about when it comes to the sun burning out. Now, there's a few other things going on that we might need to worry about, but don't worry about the sun. It's going to be around for a long time. And now Ms. Fuller is going to tell you about the electromagnetic spectrum.
Hi, boys and girls. I've got a picture here. This is of a western diamondback rattlesnake. And a lot of times when the kids come to see us and we show them the snakes we have, they don't think that they have skeletons. But if you take a x-ray of this very snake, you will see that let me put something behind it so you can see this. You will see not only does he have a skeleton, he has a very, very involved backbone and ribs, and look at that head. So yes, he's not a worm. He's very much a vertebrate. Well, how did we get that? We got that from x-rays. Well, what are x-rays? Well, x-rays are part of the electromagnetic spectrum, and that's what I'm going to be talking to you about today. So let me go ahead and share my screen with you. And here we go. So the electromagnetic spectrum, and there's our lovely sun that the other teachers have been talking about. So let's look at a couple of essential questions. Number one states, what are the 7 electromagnetic waves in order of increasing wavelength? And there's a little list of their first letters right there, GXU, VI, MR. And number 2, how does the electromagnetic spectrum affect humans? Now, most of the information that we gather about stars comes through the study of the electromagnetic waves that they emit. And astronomers gather this information with telescopes. And then they use a variety of scientific instruments to analyze the light. Now, since the end of World War II in 1945, astronomers have been able to study wave bands other than visible light. Visible light's what we see. So some wave bands like radio wave and ultraviolet actually have to be studied from outside the atmosphere of the Earth because the atmosphere helps block them, which in some cases is a really good thing. And you're going to see that as we go along. So let's talk about a mnemonic device that will help us remember the waves in the order of their increasing wavelength. So we're going to start with something really tiny gamma waves. So this is good. Xylophones use very interesting musical rhythm. And that's a very easy little mnemonic device to help you to remember those letters in the order. So here's a diagram of the electromagnetic spectrum, starting way down here with gamma rays and then going all the way up to radio waves. And in the middle, the only part that's in color is the visible light, and that's what we see. And when you were in elementary school, you learned about Roy G. Biv, the colors of the prism or the rainbow. So let's start off by talking about gamma rays. These are created and emitted from the core of our sun. The wavelength is very fast and very tiny. They're about the size of the nucleus of an atom. And how do they affect humans? Well, if a person has cancer, they can get what is called a radioactive cobalt treatment, and the gamma rays are targeted for the tumor in the person, and it will kill it. And over there on the other side, you see a picture of a celestial body and emitting gamma rays. Now, the next one is X-ray, the size of an atom. And that was the little thing I showed you, the X-ray of the rattlesnake. And X-rays are very damaging to human flesh, can give us cancer, can cause blindness, a variety of other really terrible things. It can go through soft tissue, but it reveals hard tissue. So that's why they're so good for X-rays in showing the bones inside of a human. And over on the right-hand side is a picture using X-ray radiation of what different structures in the solar system, well, in this particular case in the galaxy, look like. Now, ultraviolet light is the size of a molecule. You may have had your teeth treated for whitening. You may have been in a tanning booth. These rays are damaging. People don't seem to realize how damaging. Now, our atmosphere blocks probably most UV ray coming in, but it's why you have to wear sunglasses when you go outside, why you have to use a high SPF sunblock, because it will give you skin cancer, it will give you cataract, and it will also ruin the retina of your eye. So you need to protect yourself from UV light. And that's one of the reasons why if you're going to study the stars using UV, that telescope needs to be outside of the atmosphere, because the atmosphere would block it. And there is Saturn there being gazed upon with a telescope that is reading the UV light. Now, visible light, that's the size of a protozoan. And this is the one that we're most familiar with. Infrared, now that's the size of a pinpoint. And you can see the picture of the woman over there on the right-hand side. Infrared is dangerous. People that work with infrared have to shield themselves from it. It's what night goggles see. They see the warmth of the human body. Pit vipers, like the rattlesnake I showed you, can look at a person who may be inside of a bag or something, but he can see you perfectly because he's seeing the heat your body gives off. And microwaves are the size of a bee, and they're also damaging. You don't want to hold a cell phone up to your head too much. The picture over there on the left shows a picture of a celestial object being taken a picture of by the telescope using microwave. And then finally, we've got radio wave. Now, radio waves aren't terribly dangerous to us. They're actually pretty big. They can be bigger than a building. These are really big waves. So They range in size from radio being the size of a building all the way down to gamma rays the size of nucleus of an atom. And the larger they get, the slower they are. Way down at gamma rays are extremely fast, and then up to radio waves they are not. So let me go ahead and get out of this. And we're going to go back on up and look at our mnemonic device again, which is right here. Good xylophones use very interesting musical rhythm. This is an easy mnemonic device to remember, and it's gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwave, and then finally radio. So if you have any questions about the electromagnetic spectrum, Mr. Gorman will be more than happy to answer those for you. Have a good day.
Thank you, Ms. Fuller. Yeah, very good job of describing that. Now, a student wants to know just a brief definition or description of the electromagnetic spectrum. So I got this from earth/sky.org. The electromagnetic spectrum is the term used by scientists to describe the entire range of light that exists, from radio waves to gamma rays. Most of the light in the universe is in fact invisible to us. Light is a wave of alternating electric and magnetic fields. Thank you, Ms. Fuller. Now I'm going to stop sharing my screen. During this field trip, this virtual field trip, students described components of the universe, recognize that the sun is a medium-sized star located in a spiral arm of the Milky Way galaxy, and that the sun is many thousands of times closer to the Earth than any other star, and identified how different wavelengths of the electromagnetic spectrum are used to gain information about components in the universe. That's pretty interesting. There are components in the universe down to using it to cure cancer. Components of the universe by Mr. Monroe. The HR diagram by Ms. Nash. Ms. Ramirez talked all about the sun, and Ms. Fuller talked about the electromagnetic spectrum. Thank you. Teachers, how did we do? If you would, go to www.tiny.cc/EEC feedback, fill out a very short feedback form and send it to us. Thank you again. Y'all have a great day. You've been such a good audience. Around noon, I'm gonna bring the sun back out. Thank you.